Good afternoon, everyone. It's good to be back with you again on the podcast. And I think today's subject, we're going to talk about arc flash precautions. David McPeak hosts Incident Prevention Magazine's Institute Forum once a month. I think it's the second Friday of the month, every month, from 11 a.m. to 12 p.m. And it's always an opportunity. And they ask me many times to be on there as panelists. And I love to get on there. We usually have, I don't know, anywhere from 50 to 75 people on those programs. And a lot of questions come up. And this particular question came up, and I decided to write an article about it for, I think it's in the February issue of the magazine. So we're maybe just a tad late getting this podcast out. But anyway, it's a fascinating subject. It goes back with me all the way back in the days when I was a lineman and made a safety person, field person in the field. And we had a staff meeting one time, and it was at Auburn, I think, either Auburn or Alabama, somewhere over there. Southern Company sponsored it. Now, every one of the Southern Company safety and health specialists actually showed up at the meeting. And Hugh Hoagland was our speaker. That's the first time I ever met him, probably 95, 96, somewhere along in there. And Hugh and I got to be pretty good friends. And lo and behold, when I did retire, he asked me to be one of his presenters for ehazard.com, which is they have a very good arc flash program, and they have for high and low voltage qualified electrical worker, subpart S, lockout tagout. We go through all of that, in these programs that I put on for him. But what I'd like to do is share a little bit of that information today. One of the questions that came out of the IP forum that week was, does the NFPA 70E cover utility employees? And of course, I'll give you my pat answer. It depends on the employee. It's kind of like a political answer, I guess, but it depends on what you're doing. If you're talking about line work per se, out on the poles, no. Because it specifically says that it's low voltage. Low voltage in OSHA's opinion is 600 volts down to 51 volts. So, it does not. But if you're a utility employee, a 269 employee, but your facilities maintenance, okay, and you're working on the building and not on the utility system, the answer would be yes. All the consensus standards, the subpart S and everything else, low voltage requirements for that qualified electrical worker would be the norm. Now, the $64,000 question here is, what about solar panels? We're genning at 900 to 1,000 volts DC. And of course, we go to collectors, and then we go to inverters, and then we go to step-up transformers, and then we feed back into the system. So that one's coming up, and it keeps coming up, because when you look in generation in the standard, the 1910-269 standards, it basically relies a lot on and refers a lot on to generation of, I call it water boiling. Basically, it's, fossil plants, coal-fired plants, which are now, becoming extinct, which I think is a mistake, but that's all I'm going to say. You got to have some base loading somewhere. The wind don't always blow and the sun don't always shine, and you can't store quite enough to get the job done, but I'll let that one lie. That's what they focus on in the standard, but the actual rules and regulations, the NFPA 70E in general does not cover lineman work. It covers other types of work that occurs in the industry for sure. How best to control an arc flash, and it's like the it's like the old pyramid right here of, how do you prevent things from happening? You eliminate it. That's the surefire method. If you can put a system in an Article 120, according to the NFPA 70E, an Article 120 is an electrically safe condition by definition, and that is locked out and tagged out. That's not just turned off. That is locked out, checked for the absence and presence of voltage, and secured some manner. So, and when you look at lockout tag out on low voltage, it's found in 1910 333. Of course, in our standard, in the 269 standard, we have two. We have one for generation, paragraph D, David, and then we have one, Delta, and then we have another for transmission and distribution is paragraph M, which is really switching and tagging, de-energizing for the protection of the employee. And, there's a lot of times people kind of misunderstand. There's four kinds of lockout tag out. There's four references to lockout tag out: low voltage, high voltage, generation, and then overall all energy, which is 1910-147. The commonality with all of that is that the same locks and the same tags work for the same one, regardless of which one of the four you're locking and tagging out. The really neat thing in the NFPA 70E, there's a table in there. And this was one of the questions that came up on the forum. Does the 269 have a required table to go by, or that estimate, okay, reasonable estimate, I think is the way it's referred to in paragraph L, of the incident energy that's out there? How is there a table? Or do we have to do an engineering analysis? Or do we make, quote, reasonable estimate, unquote, whatever that looks like? Well, generally speaking, there's some factors that goes into determining the amount of incident energy out there. You're measuring incident energy in heat calories squared, okay? So, in low voltage, 1.2 cal incident energy squared, 1.2 squared will give you a second degree burn. And in basically the 269 world, the open air arcs that we're subject to on poles and structures and maybe substation, instead of a closed arc, the standard then was set to allow up to 2 cal without additional protection, which, there's a varied number of reasons why. And I'm not an engineer by any stretch of the imagination, but I would assume that it being an open air arc has a whole lot to do with that. In other words, it's a lot more room to dissipate the heat, and it's not so much directed directly at the employee like an arc in the box. The closest thing we have to an arc in the box in a utility world is going to be a self-contained meter base. When you look at a self-contained meter base, whether it's single phase or three phase, anything up to a 240 volt single phase or three phase, very difficult, from what I understand, to get above about 8 calorie. 8 cal centimeter squared is pretty bad arc, okay? And when you look at that, if it's 2 cal will get you in trouble, 8 cal is going to get you in a lot of trouble. But when you get above the 240 level and you get 277, 480, 240, 480, now you're getting to be extreme, what I call extreme. And there it is, therein lies the problem. You could have, depending on the impedance of the transformers, the size of the service conductor coming to the self-contained meter base, you could have up to probably 20 to 25 calorie, would not be out of the question, of heat. Plus there would be, 20,000 amps of fault current. Up 17, 18 is not uncommon. It all depends on, like I say, the other factors involved. The length of the service, the impedance in the power transformers or the pole transformers or the pad mount transformer that's feeding the service. So, that's my there's no table. Now there are tables, there's an appendix in 269. It requires us to make that reasonable effort. And it refers to IEEE 1084, I think it is, or ARC Pro with a 3-phase multiplier, SKM, a lot of different software out there. I just had one of my customers want a complete engineering analysis on their substations and facilities, and they, of course, I can't do that. I have to have help, and I go back again to eHazard, and I have some folks there that's what they specialize in doing, and so I just refer them over there and say, okay, you can make your reasonable effort through this company right here, and in that way, you can select the appropriate level of PPE that you need for the task that you're going to ask people to do. But yeah, the table in the low voltage is 137C 15A and B, which is AC and BC, DC. So you look at that, and it can't be specific, equipment specific. One of the things I find that folks really struggle with is, they're concerned about what they're working on, which is well taken, certainly. But it's not so much what we're working on is the real problem. The real problem is what's upstream of the device looking at what we're working on. It definitely, three factors goes into determining the amount of heat energy that's going to be developed by a short circuit, a fault in the piece of equipment we're working on. And then one of them is, there's two of the three factors you can't do anything about, okay? One of them is distance, it's reach. All the testing and when it says that it's got an 8 cal exposure, that means 8 cal at probably 18 inches. That's which is arm's length. That's the distance. You can't do anything about that. Now, the second factor that goes into that, which is fixed, and there's nothing you can do about it, very little you can do, and that is to know the available fault current. And that's determined by the upstream device. The third is going to be that's the hinge pin, that's your trunk card, and that's going to be the clearing time. Now the system, the utilities, the engineering, there's a lot of factors can go into that, but we can decrease the amount of heat energy by clearing the fault faster. And we're talking cycles here, not seconds, okay? And the difference in, 2 cycles or 4 cycles to less than a half a cycle, which is not uncommon in a current limiting fuse situation or a relay, electronic relay, like we use on distribution breakers and transmission breakers. We have a lot of Schweitzers, Coopers, Cutler Hammer, Siemens. There's a lot of similar current limiting devices out there that we can install as protected devices. Now, again, I point out to everyone, these things are not intended for the safety of the individual doing the work, because we think that individual is trained well enough and use the correct PPE and the correct protective equipment that it's going to take care of us. Now, I guess the benefit to the current limiting clearing time decrease is going to be, it doesn't hurt us as bad as if something goes wrong. And that's the benefit that we're the benefactors of that faster clearing time. You'd be surprised. I mean, when there's 60 cycles a second and it takes 2 to 4 cycles to start realizing there's a fault, okay, and then another 2 cycles to actually start implementing a clearing device or a fuse blowing or a relay. And if it's not current limiting, and it's not reset relays. Now, when you reset that relay to start clearing in a half a cycle, about 83/10,000ths of a second, that just decreases the amount of exposure to the individual, to the equipment, to the system, to everything. As I said, we're secondary to it, but we're a benefit of it for sure. So, yeah, that's one of the things that I always wanted to point out when I talk to people is, yes, the NFPA 70E has that table. If you're looking at a 240 amp split bus main lug disconnect panel, whatever, and main breaker panel. And, you know, it's not going to have anything on it from the manufacturer. It's got to be engineering analysis and that reasonable estimate made, or engineering analysis made when it's put in, because you got to look at what's upstream to determine if it meets the criteria to use the table 137 C15 A and B. And if it doesn't meet that criteria, if it's not under the certain amount of 25 or 28,000 amps of fault current, you can't use the table. You're going to have to do an engineering analysis on it. So, and then again, too, the appendix, I think it's Appendix E in the 269 standard, is helps us here in tables 6 and 7, the flash tables that's in there, that requires us to use either ARC Pro or IEEE 1084 or something. These tables here will help us in estimating that heat energy. And, you know, and the thing about it is, another thing too, that, and I tried to explain this to a lot of my customers, if you got a substation out there with 5 breakers in it, and 1 power transformer is feeding that 5 breakers, the reasonable estimate right here would be on 1 or 2 of those breakers, because unless there's some drastic equipment changes, it's all going to be about the same. And I think most of the time, what I find is what they're telling me is if it's 12 or 25 kV distribution circuits, usually about 8,000 amps of available fault current and 8 cal if you size your grounds to the 8,000 amps of fault current, and then you size your PPE to the 8 cal incident energy, you're going to come out of it pretty good as far as protective devices and meeting what the regulation requires. So it's one of those things. Like I said, the self-contained meter base, I can't put enough emphasis on that whatsoever. You know, and this goes all the way back to the National Safety Council and the NESC estimates back in the 2005 and 6 time, when EPRI was doing the testing for them, and they were trying to come up with the estimated amount of heat energy under certain conditions. And that's when they come up to anywhere within 17 to 18 on the low side and up to 20 something cal on the high side. And these are self-contained meter bases of 277, 480. And as I said earlier, the 12208, 12240 meter bases, self-contained meter bases will not be quite that high. Another subject that came up in the IP forum was the UD transformer and switching. Of course, the switching is often one of those things that you can get an ejected arc in a switching event. It's not just a flash, but like a bushing fails, you pull an elbow off of an underground transformer, you could have what's called an ejected arc. It'd be like a cannon shot. And of course, where are you standing? Switching it right in front of it. So you really have to make sure, you know, and just remember the 18 inches. Of course, you're on the end of a 6-foot stick. There's so many factors that goes into this, you know. We just had an incident. I think I just read an incident where there was a fatality, and it was switching in a live front underground device of some kind. I don't know whether it was a switching cubicle or a live front transformer. More than likely it was a switching cubicle. And basically they actually tripped and fell into it and actually had a contact, not just a flash. But many times in switching cubicles, and I try not to mention names of manufacturers because I don't want to make it look like one's any better than the other one, but we've had our issues with switching cubicles in the past with fiberglass partitions, either getting loose or falling into the hot side of the switch and causing, you know, problems and faults. So whenever you open the door of a transformer, you need to be very particular, make them good inspection. And of course, I strongly, to prevent any kind of arc flash exposure, you know, use your PPE, you know, your minimum 8 cal, whatever, I would not do it anything less than 8 cal on a live front transformer or a switching cubicle. But use, hard hat, rubber gloves until you get the door open and you can inspect it to be sure. Then you maintain minimum approach distance on it with sticks. That's the there was a company that was using a 4-foot shotgun stick. And I know in situations where people's planted things and built buildings in front of transformers and done all kinds of stuff, we have these issues that we have to deal with. But you remember, if you got a 4-foot stick and you choke up on it to do the switching, and you've got an energized, say a small interface 25 kV elbow, and you're coming off, there's going to be a point in time to when you're almost violating minimum approach distance. Even with rubber gloves on, you might, it depends on your standing position. But just be careful when you're doing that, because that's just good advice. That's the only thing I can tell you there. Now, substation entry, some companies require full appropriate PPE to enter the substation. And I guess this is a preventive measure to keep anything from happening or scope of work changing while you're in the, say I'm going to enter the substation and all I'm going to do is go to the substation house. Say I'm going to go to the control house and I'm going to get a reading or whatever I'm going to do, or I'm going to work on the HVAC, or I'm going to do something. Well, am I subject to arc flash? Well, where's that 2 cal boundary? Where is that magic point? Not a MAD now. We're not talking about MAD, minimum approach distances. We're talking about that distance from an exposed energized part that could fail, an insulator or bushing or a device that would cause an arc, where I could receive 2 cal centimeters squared incident energy. At that point, I got to have on PPE. Now, where's that at? I mean, you may be 25 feet, from the nearest distribution breaker or regulator, but you get next to an LTC, or you get next to a 115 or 230, 345 breaker. Where's that at? And that's the beauty part of what the 269 requires, when it tells us we've got to make that reasonable estimate in there and make that determination. Why a lot of companies just say, look, you're going to enter the substation, you're going to do a substation inspection, do a job briefing, you're going to walk in and you're going to be dressed out in all your PPE. And then some don't. I was in a substation not too long ago and did some substation entry training, and there we were. And I said, well, do you require PPE to enter a substation? Well, no, not if you're not going to do any switching. And that's not uncommon. So it's ever how the employer wants to interpret the rule, and also the amount of risk that you're willing to accept. And I think that's the main thing. Well, I've probably taken my 20 minutes or so, or getting close to it anyway. And I was hoping that we could get through this part of it here today and, share just a little bit about this arc flash phenomena that we deal with every day. And I'll say this last little story, and I'm a storyteller. Read my book if you don't believe it. But I had one really bad flash when I was a lineman, and I write about it in the book. And for forever and a day, I could not figure out why I was not hurt worse than what I was. And it was a 7.2 kV phase to ground flash, 4 spans from a substation. I was told it was about 8,000 amps fault current, or just less than that far away from the substation. I mean, I could hit the substation with a rock almost. But we were trying to take a slack out of a piece of 1/0 ACSR, and it was insulator was mounted vertical on a steel arm. And of course, we were so concerned. The lineman and I was a junior lineman, hadn't been a lineman about a year, 73 is when it was. And I had been a lineman about a year, and Gene, the guy that I was with, Gene, he said, well, let's do this. And I said, well, let's do this. So we kind of figured it out. And what it was a weird thing. It always It's always, you get focused on one thing and it draws your attention away from the actual. And this was a slack span with a flat to vertical slack span. And the vertical was on the mainline pull off, and the slack span went over about 20 feet over to a pole, and then it was guide from that point on. It took off at a different angle, and they just couldn't put a guide down on the mainline pole because of the road, the way the road configuration and the intersection was. So they just slack spanned it over there. Well, series of events led up to the fact, other than the fact that I didn't cover it up appropriately, because we were so concerned about the slack wire, because it had been reported that it was getting together if the wind blew. So we didn't want to take a chance of covering anything up or doing nothing. It was only 20 feet long or less. And I told Gene, I said, hold it, just hold it. Let me slack this nut off right here, and we'll slide the wire through the clamp and take up just enough to where we can tighten it back down and keep it from getting into something, because they was going to have to come in there and put down new guys and everything. They had let the guys get away from them, and they were not in the right position, and the pole was leaning. There was just a bunch of stuff going on. And we all agreed that that was what we should do. Well, we started the job and started the work, and I took a split blanket, a 36 by 36 split blanket, and I wrapped around the base of that insulator on the end of that steel arm. And I was watching Gene raise the phase. I raised the clamp up because it was almost hanging down. It was so slack, and put my wrench under there to slack the nuts off of that slack span clamp. And I had left the corner of the steel arm sticking in just outside the split blanket. And when I did, the wrench contacted the arm and we had a flash. Now, it would have been bad enough just to stick the wrench against the steel arm, but unfortunately, when they framed the pole, not only did they put the guys down in the wrong place and let the pole get away from them, they let the pole ground get under the gain on the steel arm. And of course, now it's a direct path to the neutral. What I couldn't figure out for a very long time was, why did I get burned worse? I mean, I'm right there, probably less than 18 inches. Now, distance and heat is inversely proportionate to one another. If you double the distance, you cut the heat in half. If you shorten the distance, you increase the heat. So I'm holding that wrench and doing that, boom, and it blew up. But I only got a 1st degree burn. I had a little bit of a 2nd degree burn above my rubber glove and below my t-shirt that I had on at the time. Of course, this is before ARC rated FR clothing or anything else. And I said, well, why didn't it burn me worse? But then it dawned on me. The flash really occurred at the pole ground on the pole about 4.5 feet from the end of the arm. And I was in other words, I was 6.5, 7 feet away from it instead of 18 inches. So the inversely proportion to distance to heat basically worked itself right out right there. It was an open air arc. It was almost 6 feet away from me instead of 18 inches, okay? So that cut it from the 8 cal probably down to less than 2. Now, let me tell you something, it was hot. I can assure you that it was hot, and it was loud, and it was colorful, okay? I never will forget it. And it was one of the things that kind of burned in my memory, if you will, a pun, that why I am so picky about cover up now and protecting people from arcs and flames, because you just don't want to go there. And I've also seen way too many people get hurt since because of it. And so that's my personal testimony to kind of back up what we've been talking about right here. So with that, I'm going to end the podcast for today, and thank you for listening. My goodness, I wish I could see everybody at one time. I will invite you to come to Schaumburg, Illinois in May, and we will be doing, I think we're doing contractor management there, I believe, host contractor management. But we will be there all week, and we'll be talking to everybody. And I'm looking forward, since I've missed the last 2 meetings, and I'm looking forward to seeing all of the IP folks and all the people, the attendees that comes to that meeting. So God bless you. Take care, and we'll see you soon.
The views, information, and opinions expressed during this podcast are solely those of the individuals involved and do not necessarily represent those of Utility Business Media and its employees. It is strongly recommended that you discuss any actions or policy changes with your company management prior to implementation.